Let's talk about some properties of the Laplace transform. These are in section 4.2 of your text. Laplace transform properties. Again, knowing a few properties and a few algebraic tricks, you can greatly extend the usefulness of our Laplace transform table. So again, here's the notation we'll use. Our time domain function, lowercase x of t, has Laplace transform, uppercase x of s. Let's look at the time shifting property. This is a quite common operation, but if, for example, we are dealing with a shifted version of x of t, a time-shifted version of x of t, then its Laplace transform will be the Laplace transform of the unshifted x of t, which we call x of s, times e to the minus s t0, where minus t0 here is our time shift. To emphasize the causality of x of t, typically write this like this, u of t minus t0, that transforms as above. Let's look at a few examples, and I'll illustrate some of the common algebraic tricks that are involved in applying time shifting. So, for example, if we've got x of t is e to the minus t minus 4, u of t minus 4. This one's straightforward. You know, a related unshifted function would be e to the minus t u of t, and the corresponding Laplace transform from our table, I think we did this by direct integration last time, is 1 over s plus 1. Okay. And then, so now since x of t is actually g of t minus 4, then x of s would be equal to g of s times e to the minus 4s, or we get e to the minus 4s times 1 over s plus 1 here for the Laplace transform of x of t above. A related example, let's assume x of t is equal to e to the minus t minus 4 times u of t. Okay. And we want to find its Laplace transform. This is not actually a time-shifted function. There's a t minus 4 here, but we can actually rewrite this as e to the plus 4 times e to the t u of t. Okay. And this is the same as our g of t above. So again, here splitting this out, doing this little algebraic trick, again, emphasizes that x of t actually is non-zero for all t greater than 0, and it's not a time-shifted function. So the corresponding x of s would just be this constant, e to the 4 times g of s, since this part is equal to g of t above. So the transform of this function is just e to the 4th power times 1 over s plus 1. Another related example is if x of t is equal to e to the minus t u of t minus 4. Now, this is a time-shifted function. It becomes non-zero at t equal to 4. But I'm going to have to play a little algebra trick to get the time shift here in the exponent. That's easy to do. I can just subtract 4 and add 4, u of t minus 4. And so this becomes, I'll pull the plus 4 term out, so with the minus sign in front of it, e to the minus t minus 4 u of t minus 4. Okay, so now this is a time-shifted function. X of t is just e to the minus 4 times this time-shifted function. We already found the Laplace transform of the time-shifted function. It was in part A. So the Laplace transform then would just be e to the minus 4 times the Laplace transform that we found in part A. It's e to the minus 4s times 1 over s plus 1. I can combine the exponents here as e to the minus 4s minus 4 times 1 over s plus 1. And I could simplify a little bit more if I wanted to. By factoring out the minus 4, I'll have s plus 1 over 1 over s plus 1 here for that final result. So these algebraic tricks come in handy. They're not applicable only to exponentials. So let's take a look at another example. X of t is t minus 4 times u of t. Again, this is not really a time-shifted function because it is non-zero for all t greater than 0. Here I just expand this. I'll have t u of t minus 4 u of t. And both of these are directly in my table of Laplace transforms. The t u of t becomes 1 over s squared. 4 u of t actually has a transform of 4 over s. I can combine these over a common denominator, which would be s squared in this case, and I'll have 1 here, and then minus 4s here. This is fine, or typically we'd write these as a ratio of polynomials in such a way that the leading coefficient of the highest order term is equal to 1, and so I can actually factor out a minus 4 out of the numerator and be left with s minus 1/4 over s squared. So this would be the representation in a more standard form. Related example would be t times u of t minus 4. Again, this is a time-shifted function. It's non-zero only for t greater than 4. So I've got the time shift here of t minus 4. I'd like to introduce a time shift here. I can do that. It's a little algebra trick or a math trick. No algebra actually involved. And then write this as t minus 4 u of t minus 4 plus 4 times u of t minus 4. And this is just a straightforward time shift of t u of t. T u of t has a transform of 1 over s squared to account for the time shift. Here it would just be multiplying by e to the minus 4s, and then 4 u of t, we found that transform previously as well. That's 4 over s. Again, this is a time-shifted version, so I'd have to multiply by e to the minus 4s. Again, I could do a little algebra here, combining things over. Factor out an e to the minus 4s, combine terms, and this simplifies to e to the minus 4s times s plus 1 over 4 over s squared. So I'll let you work through the algebra there. Two other properties I want to talk about quickly in in this video. One is, it's known as the frequency shifting property, sometimes also called the modulation property. We saw how a time shift led to multiplication by an exponential in the Laplace domain. Similarly, multiplying in the time domain by an exponential, that leads to a shift of the Laplace transform in the S domain. So this is the frequency shifting property, also called time modulation. And finally, the last property we'll look at here is time differentiation. dx dt transforms as s x of s minus little x, so this is the time domain function evaluated at 0 minus. Recall that our transform definition extends from 0 minus. Further extend this to the second derivative of x with respect to t transforms as, it would be this times s, so we'd have s squared x of s minus s x of 0 minus, and then minus now the first derivative, which I'll just denote as x dot because the notation's a little simpler, evaluated at 0 minus, and then and so on and so forth. You could extend this on to third and fourth order derivatives. We'll look at some additional properties of the Laplace transform in the next video.